Hi, everybody. My name's Alex. Super excited to be here. First time visiting Budapest, so a lot of fun. Huge thank you to the organizers for making this happen. A little bit about me. I write a lot of Python open source code. I serve as a board member for the Python Software Foundation, and I work at a company called Rackspace. So first question is, why would you ever want to build a Ruby interpreter in Python? There's many, many perfectly functional Ruby interpreters. There's MRI, JRuby, IronRuby, Rubinius, and probably some more I'm not even thinking of. So the story of why I was interested in this starts probably about a year and a half ago, maybe 2 years. A friend of mine was actually building a PHP interpreter in Python. And that looked like a lot of fun. I was doing some code review for him, reviewing it from the beginning. And I'd worked on a lot of interpreters before. I'd worked on CPython. And so I understood what I was doing reviewing his code. But watching this, I realized I'd never actually written an interpreter from scratch. I'd always contributed to an existing one. So I decided it looked like fun. And so that's where I got started. I was like, this is fun. I should try this out. Ruby's a popular language. I don't think anyone's written a Ruby interpreter in Python. I should do it. The second explanation was I work on a project called RPython, and building a Ruby for it is a cool demo. And the last reason, perhaps the least exciting, is there's a really small minority of people who get really mad when they find out a Python person is writing this Ruby interpreter, and I just think that's funny. And so the reason someone might possibly care about it is performance. By building a Ruby interpreter in Python, I thought we could get better performance, which is a thing because a lot of people believe Ruby is slow. And Ruby is slow is kind of not a very precise statement. It doesn't really explain what we mean because Ruby's a programming language. Ruby's not a program, really. So we be a little more precise. We mean C Ruby, which in fact is the Ruby program on most people's computers. But it's not inherent. There's no reason Ruby has to be slow. And what is it slow at? So C Ruby tends to be slow at executing CPU-bound code. So C Ruby can read and write from disk as fast as anything. Reading and writing from disk the speed is not about what programming language you're using. And but a lot of people write programs that do use their CPU from time to time. So on programs people commonly write, C Ruby's not as fast as we'd like it to be. Or more shortly, a lot of people want Rails to be faster. And so when you talk to people about the fact that Ruby or Python or JavaScript or any other dynamic language is slow, you get a lot of sort of really bad responses in my experience. You get responses like, our app is I/O bound. And so we don't care that Ruby is slow because we're not doing CPU bound things. And in my experience, that's not usually the case. We say our app is I/O bound, but actually you can find 30% or bigger wins. We also hear, yeah, we know it's slow, but we'll make it up with programmer productivity, which I think is true. I think a lot of us here believe that we can make it up with programmer productivity, but it's not a response to, Ruby is slow. That's just a thing we believe, and it's important to care about how programmers work. And the last answer, and the one that makes me really sad, is you say this to some people, and they'll say, yeah, we know it's slow, but we'll rewrite it later. Once we're big, once we actually care about speed, then we can just rewrite everything. That makes me sad because I like dynamic languages a lot, and I wish people wouldn't just assume that rewriting it was a great answer. So it's slow, but why is that? And I think there's actually two ways to read this question. One is, why is Ruby slower than some other programming language? Why is C Ruby slower than Java or C or something like that? And the other question we might ask is, why is it slower than it could be? If you just start talking to people, why is Ruby slow? The always answer you get with any dynamic language is, the compiler doesn't know the types. It's a dynamic language. We read the source code. We don't know what types variables have. Okay, that's true. Okay, so that makes it slow. What does that actually mean? What can you not actually do as a result of not knowing the types? So some of the things that happen are all function calls are indirect. Instead of in a C program, you might emit a call directly to some address in memory where there's some assembler. Instead, you're jumping to some random unknown location. And in practice, it's even worse than that. Because when we say function calls are indirect in languages like Python or Ruby, what we really mean is there's probably a hash table lookup to look it up from globals, to look it up as a method on some object. So that takes some time. And if you saw James Gollick's talk this morning, he talked a lot about the amount of time that's wasted looking up methods in Ruby. We end up with a situation where all of our containers, arrays, hashes, they're all of objects. They're not of some specific type. So whereas in C, we might have an array of floats, which is, each one is exactly 4 bytes long. And so if we have an array of 10 floats, we take 40 bytes. In C Ruby or CPython or any of these interpreters, what we actually end up with is an array of pointers to objects which contain floats. And so that's a lot of extra memory used. That's a lot of indirections. That takes some time. And lastly, things like instance variable lookups. Instead of whereas in C, you can compute exactly what offset something is at in memory. So you can just say, oh, I know that's 4 bytes away from the start of the struct. We can't do that in languages like Ruby because you can add or change exactly what instance variable something has at any time. So we end up with, we have these hash table lookups on every instance variable. So what if we were to design a fast Ruby? The exact same programming language, but write a new implementation of it that addressed these problems, that didn't have these hash table lookups, that used less memory, that addressed these constraints. And to do it, we're going to look at doing this in a tool in a language called RPython. RPython is a programming language. It's pretty unpopular. It's a statically typed programming language. It has type inference. It's got a garbage collector, a pretty good one, nice generational garbage collector. And the syntax is actually the same as Python. And I have to tell you, there's almost no reason you should ever use this language. This is a terrible programming language. There are so many good programming languages that have these properties. There's no reason you would want to use this. It's inconvenient. The compilation times are terrible. The error messages are even worse. It's not a fun thing to program. But it's got one feature that absolutely nothing has. RPython comes with a just-in-time compiler generator. What that means is it can take any interpreter you write in it and automatically generate a just-in-time compiler that will generate machine code for your language. And in addition, it has some useful tools that make it really easy to build high-performance implementations of these dynamic languages on top of it. So RPython has what's called a tracing just-in-time compiler. And you might have heard of these. Probably the most famous tracing just-in-time compiler was something called TraceMonkey, which for a number of years was the just-in-time compiler inside Firefox. Another one you might have heard of is LuaJIT 2. And so the basic idea behind tracing JITs is that most times when you run most code, it's similar across runs. It doesn't have to be. There's nothing about Ruby that says this variable will always be an int. But in practice, it usually is. And so the JIT will observe exactly what code is being run and figure out what code is really hot, what loop is being run tens of thousands of times. And then it will observe exactly what that loop does, and it will generate some assembler for it. And then hopefully we can run that assembler much more quickly than normal interpretation. So this is direct machine code we have at the end. And so we'd start with some code that looks like this. This is some RPython code. So these are real machine integers, so that n takes up 4 or 8 bytes on your CPU, really small. And so if we were to compile this loop with RPython's tracing just-in-time compiler, it would look something like this. So we start, and we've got a loop, and the variable that comes into the loop is n. And the first thing we do is check if n is not equal to 1. And then we have a guard that that's true. And the idea behind guards is there are a lot of paths in dynamic languages that are rarely taken. There's this type might not be what I expected. And it's possible, but it's really rare. So we have this guard that basically lets us say, from here on afterwards, for all the rest of the instructions after the guard, we don't pretend that case never happens. Pretend n is always not equal to 1. And if it's actually equal to 1, that guard will jump somewhere else. Some other code will handle that case. We don't need to worry about it in what we're dealing with. So we check that n is not equal to 1, and we have this guard. Make sure that is always the case, that n is not equal to 1. And then we perform a binary AND with 1, check if the result of that is equal to 0. And we can see each of these variables has a magic name, just I with a number counting upwards, because there's no variables in our program that have these names. And so we check if it's equal to 0, and we guard true. We guard that it's true. And of course, it's possible that on the next iteration, it won't be true. In fact, what we'll do is we'll divide n by 2. So we'll get n equals 5. and then n and 1 will actually not be 0. So the next iteration, something else will happen. But we don't care for now. Finally, we'll divide by 2, and we'll jump back to the top of the loop. And so the key thing to understanding why dynamic languages are slow is that we need to be able to communicate to the system that there are things that are probably, almost certainly true. And this is the case in dynamic languages. Yes, I could pass any type here, but in fact, I always pass an int. Yes, this array could contain any types, but in practice, it always contains my active record model. And there's really no parallel to this in statically typed languages. In Java, your class always has the same set of fields. You never sometimes have different fields. Dynamic languages are all about maybe. And so this is sort of what the Ruby object model looks like if we wrote it down in Python. It's really simplified. If you just look at this, you can see our class is missing tons of things. We don't have a superclass. We don't have module inclusion. We don't have constants. We don't have any other things that give us Ruby's rich object model. But we have a very basic thing. So if we actually start from the bottom, so we have some instances, and they have a class. And the one operation we can do on this instance in our really simplified model is we can send them a message. And we can't even send something with arguments. We can just send a method name. And what is sending? Well, we find the method on our class, and then we call that method with ourselves. Very simple. And how do we find a method? Well, a class is a dictionary, and the dictionary maps names to methods. Very simple. Unfortunately, this is also really slow, because that dictionary lookup, every one costs you about 40 nanoseconds. It doesn't sound like a lot. You got 1 billion nanoseconds in 1 second. But if you have to do this for every single operation in your programming language, it all adds up pretty quickly. So we want to find a way to get rid of this dictionary lookup, to remove the hash table lookup, because it's just a burden on us. It's just time spent doing something that's not running your program, really. And so to do that, let's take a look at sort of what tools RPython gives us to enable us to express the maybiness of this. Because almost every time with a given class and a given name, we're going to find the same method. But we don't have to, right? Someone can come in and monkey patch our class, give us a different method, change it up at any time. But they probably won't. In practice, that doesn't actually happen. So the first tool RPython gives us is a decorator called jit.elidable. And elidable is not really a term most people have heard. If you're a functional programmer, you might know the term referential transparency. And that's what this really is. What that means is that a function that you use this on is required to be able to be replaced with its result. It doesn't do anything. It doesn't change anything in memory. It doesn't print something to standard out. It doesn't do anything but a compute a result. And it's got one slight wrinkle, that it's allowed to do something like caching as well. But mostly, it should just always just compute a result and not do anything else. So with a tool like this, our first instinct might be to write some code like this. Always replace the result of find method with some known value. Unfortunately, even though this is really simple and looks great, it doesn't work in practice. Because what happens is, if we replace find method with its result, and then we come in and, and then we monkey patch the class, then we're going to have the wrong result from find method saved. And so we need to somehow be responsive to the fact that we can monkey patch out from under ourselves at any time. So the next tool RPython gives us is called promotion. And basically the idea behind promotion is when you're tracing, when you're observing every single operation, note what a specific value was and generate a guard. So if we have this function f and we call jit.promotex in it, and then we call f with 10, the actual code that will be generated will check that x, whatever value x has later, will check that it's equal to 10, and we'll guard on that. And then something else will happen, whatever else f does. And so this lets us generate the idea that some things should always be the same in a given path, like the class of an object, for example. The last tool we have is something called quasi-immutable fields. These are my favorite things. It's just such a great name. And the syntax is a little bit confusing. So what does this mean? The idea is sometimes we have one of these things that almost never changes. Almost is a kind of a recurring theme here. So what do? We perform a pretty neat trick. instead of emitting code to read the value from memory to look up this field every time, the JIT actually won't generate any code when you try to read this field. If you access .field, no code will be emitted. Instead, the JIT will take note of that fact. And if you later go to write to field at any time, it'll invalidate the assembler that's generated. It'll just say, oh, you changed this? Now the assembly I generated is no good anymore. Just invalidate it, get rid of it, and maybe we'll try to compile something again later. So we've got these three tools. And though they may look kind of strange, kind of different, it's not clear how to connect them all, it turns out we can implement every sort of semantic for a dynamic language we want, just in terms of these three tricks. And that's because they compose really nicely. Even though they look unrelated, we can combine them in really interesting ways. So what does actually doing an optimized method look like? Looks like this. So what's changed? So we made a few different changes. You can see first we declared this version field on a class to be quasi-immutable, and we added a version field to every class. It starts at 0. And every time we add a method now, we increment it by 1. So we have a different version every time we monkey patch this class. And we rewrote find method to be a little bit different. Now it just calls this underFind method and also passes along version. But if we look at the code for find method, or underFind method, I should say, we can see that version's actually never used. More on that later. And then if we look at the code for send on an instance, we can see we've added promotion of the class and the name, the method we're sending to. So how does this all work? So let's say we have some code like this. Really simple, common. Probably you have code like this on almost every line of your Ruby programs. So let's look what happens if we try to compile this simple send to a method on my object. So we're going to step through this line by line and see exactly what code gets generated. So the first thing we do is we promote this class. So we have this get field operation. Just reads this class field out of my object, a simple like one assembly instruction move. So we read that out, and then we check if it's equal to some class that we observed, my class, and we guard that it's true. We're only interested in cases where my object has this specific class. And then we promote the name, and this is something similar. We check if the string a method is equal to the observed a method, which it always is in our program, and we guard true. And then we go into find method, and we emit a get field for this version. So we also need to look up the version field from our class, and then we call underFind method with our class, the name of the method, and the version, each as arguments. So this is what we've emitted. And looks like right now maybe we haven't made any progress because underFind method does the same hash table lookup, same dict lookup as we had in the first place. Looks like we've moved around a lot of code, added some, but haven't actually fixed anything. So what happens? Let's see what happens when the optimizer starts looking at this code and seeing how it can improve it. So the first thing it notices is that the string a method is always the same as a method. So we can get rid of that. We know that that's always true. And so then we end up with guard true true. And true is always true, as it turns out. So we can just get rid of that operation. Just delete it. So now we've got this. And the next thing we notice is because we guarded that P0 was equal to something, we can just replace P0 with the value we know it has. We know we're trying to read the version field from my class. And because the version field is quasi-immutable, we can replace it with some value we've observed. So we can just get rid of that entirely. And so now we're calling find method with our class, which we know about, the name of the method, which we know, and the version, which we know. And if we've observed some previous result, now we're okay. So we can just replace this. And now we've only got 3 instructions where we used to have a lot more. So what happened? What was the trick we played? Before, if we just tried to put jit.elidable on find method, it would be wrong because someone could have changed what methods we have. Now what happens if we call underFind method is we've got the version, and the version will always match the method. So if I call this with version 10 and then I monkey patch it later, that basically the version will no longer be 10. So we'll have invalidated the assembler. So we'll never try to call this with a different version. The version lets us keep track of whether basically our cache is valid or not in a really inexpensive way. So we've got 3 instructions, and it turns out these map exactly almost to 3 assembly instructions, which is considerably better. So this is probably measured in under 5 nanoseconds, probably even less on modern CPU. And it turns out the same trick applies to constants in Ruby. Don't let the name fool you. Constants are, in fact, not constant in Ruby. You can change a constant at any time. So we can use this same trick to replace our constant lookups with almost no work. And so I got really interested in building this, and so I built a project called Topaz, which you can see at topazruby.com. And it's a Ruby interpreter that's built, and it uses these tricks to try to optimize Ruby code. And so right now the status is Topaz is very fast. It runs many benchmarks 5 times or 20 times faster than CRuby. It's also very incomplete. It's missing all sorts of methods on classes like string or IO, array. There's all sorts of things missing. Almost none of the standard lib is there, for example. And so in practice, it can't run much real Ruby code. Definitely can't run Rails, for example. The good thing is, all of you are going to help, I believe. So the future, which I'm very much looking forward to, is we'll expand the amount of Ruby code this can run. We'll be able to run gems, so people can actually install packages with it. We'll be able to run Rails, which it turns out is what I've been told most Ruby people want to do. And the really exciting thing, in my opinion, is that we'll be able to do interoperability with Python. Just writing this interpreter in RPython doesn't give us interoperability, the same way that the fact that MRI is written in C and CRuby or CPython is also written in C doesn't give us interoperability for free. But it does give us some advantages. For example, we can share the garbage collector between Ruby and Python, and that lets us simplify some things. So I really look forward to being able to interoperate between the two of these. So thank you guys very much, and I think we have time for questions. Yeah.
I understand that your interpreter is not complete yet, but once it is, can you foresee some advantages that MRI will still have against your interpreter?
Sure, so that's a great question. What advantages might MRI still have once this is more complete? And this is a question we constantly experience. I also work on PyPy, which is basically a similar effort, but for Python. And we get a lot of the same questions. PyPy is now very complete, but still not everyone uses it. Why is that? And the biggest answer is that not everyone just writes Ruby code. Not everyone just writes Python code. Turns out we also write a lot of C code that makes a lot of assumptions. We write C extensions to bind to things like MySQL, Postgres, some scientific library, things like that. And extensions like this won't just work. So I'd encourage people who have extensions like that to look into using libraries like FFI to integrate with C code, because that will also work on JRuby and Rubinius and Topaz. So that'll work everywhere. But that's probably the biggest advantage MRI will have. Performance-wise, I can imagine you could craft some devilish code that never did the same thing twice, so all of the assumptions are wrong. But I would not expect for any real code for MRI to have a serious performance advantage once this is done. Yeah.
Since the since the interpreter is not complete yet, that you can actually run anything with, how are you benchmarking for speed?
Sure, that's a great question. Benchmarking is a super challenging task. Thus far, we've been using what a guy named, can't remember his name actually, First name starts with an A, last name starts with a C. I know that's real helpful. He put together a number of years ago a big suite of benchmarks that I know people from the Rubinius team and JRuby team have also been looking at. And so of those benchmarks, the ones that we can run, we've been using those to measure our speed thus far. We also do pretty aggressive unit testing to measure performance. So we actually write unit tests to make sure that the exact operations we expect are generated. And so we can do sort of analytic understanding. If we have some regression, we start generating more operations than expected. We don't know exactly how much slower, but we know it's slower, so that also gives us insight.
Have you run Ruby spec, like the ones that you can run against your stuff, and what's the completeness level there?
Yeah, so Ruby spec is a project that was started by the Rubinius team, basically with the idea of what if we had an executable test suite, an executable specification. So anyone with a Ruby interpreter could run it and say, hey, I can prove that my string.split method does the right thing. And so, yeah, we've been using that from the start to measure our progress. And right now we pass something like 8,000 specs. I don't know what the total number is, but we pass a lot of them. And we use it to continue to measure our progress. Any other questions?
Mechanism that is more favorable than having a virtual machine for a statically typed language?
Sure. So the question was, how does Topaz compare to JRuby, and is there any advantages RPython has over something like the JVM, which was originally designed for a statically typed language? And so the answer is we're faster, but much less complete than JRuby on code I've seen so far. And RPython has a lot of advantages over something like the JVM in that it was designed for dynamic languages first. So it has these tools from the ground up. The flip side of that is the JVM team at Oracle has been rapidly trying to improve this. So a number of years ago, they added a tool that was called Invoke Dynamic that was really important to improving JRuby's performance. And right now, they have an internal project called Truffle and Graal, which are supposed to give really huge performance improvements, actually. They've showed off a demo interpreter that's something like 5 times faster than JRuby, a little bit faster than Topaz even. It's not open source yet, so I haven't really reviewed it to see if, maybe there's something we can steal to get the lead again. But yeah, so there's nothing inherent about statically typed VMs that makes this impossible. It's just that they're usually missing the tools. And it's possible to go in and add those tools later. All right, thank you guys so much, and I hope you guys will all contribute to Topaz.